Hello, everyone. Welcome to this presentation. My name is Zhiwei, and I'm a PhD student at Rice University working with Professor Moshe Barty. Today, I'm going to present studying a quantum graph problem by logic and combinatorial optimization. This presentation is recorded for the quantum graph best paper for 2023 by Max Planck Institute for the Science of Light. I also want to thank Maria Korean for inviting me to do this recording. So the outline of this presentation is as follows. We first give an introduction of the quantum graph problem and the Crane's conjecture. Then we give a simplified version of generalized Crane's conjecture as graph theoretic decision problems. Then we show some theoretical analysis of the problems as well as practical methods based on logic and combinatorial optimization. The object that we study in this research is a special class of graphs with bicolored edges, where each edge can have up to two colors. For example, on the top, this edge is colored half blue and half green, and the left edge is colored with green only. And also, multiple edges can exist between the same pair of vertices. A perfect matching is defined as rule, which is a set of independent edges that covers all vertices. For example, in this graph, there are four perfect matchings, which we list on the right. Notice that although in the graph, it's the edges that are colored, every perfect matching corresponds to a unique vertex coloring. And we can define the vertex coloring for each perfect matching as follows. Each vertex obtains the color from the half edge that is adjacent to it in the perfect matching. For example, in the first perfect matching and for the top left vertex, the vertex color of it is green because of the half edge that is connected to it is colored green in the perfect matching. In the original definition of the quantum graph problems, there is also the concept of weights for edges, perfect matchings, and the vertex colorings. Each edge can have a weight as a complex number, and the weight of a perfect matching is the product of weights of all its edges. And the weight of a vertex coloring, let's say C, is the total weight of all perfect matchings with that coloring. So for example, in this graph, we have assigned a complex number as a weight to each edge. Then for those four perfect matchings, we can compute the weights of them. For example, the first perfect matching has weight 1, which is the weight of the green edge, times 3, which is the weight of the purely red edge. So the weight of the perfect matching of this perfect matching is 3. And for the second one, we have the weight of the top edge as I, which is the imaginary number unit. And the bottom edge have weight 1 plus I. So the weight of this perfect matching is I minus 1, so on and so forth. And for the weight of vertex coloring, we have that for the first and the third coloring, there is only one perfect matching exists. So the weight of those vertex coloring is just the weight of the perfect matchings. And for the second vertex coloring, it has two perfect matchings. So the weight of this coloring should be the total weight of all its perfect matchings, which is I minus 1 plus minus 1, which is I minus 2. So now we are ready to define the general graph theoretic problem. We say that a graph G, here by a graph G, we mean graph with bicolored edges, satisfies a quantum state represented by a set of vertex colorings, capital C, if the following two conditions hold. The first condition is that for each coloring C in capital C, the total weight of that coloring is 1. And for each coloring that is not in capital C, the total weight of that coloring is 0. And the problem now is defined as given a quantum state represented by a set of vertex coloring C, can we construct or prove the non-existence of a graph which satisfies C? As you can see, the definition of the problem defined in the last slide is quite general. It lets you to define a quantum state with an arbitrary set C. But there are some specification of C that has quantum interest. For example, the GHZ state and the corresponding Crane's conjecture. So in the GHZ state, C is defined to be the set of all monochromatic colorings. For example, if the number of vertices is 4 and the number of colors is 3, then we have this graph. Then we claim that this graph satisfies the GHZ state. Why? Because if you check all three monochromatic colorings, which are all blue, all green, and all red, you can see that the weights of those colorings are all 1. And besides, there are no other perfect matchings with a non-monochromatic coloring. So for all colorings that is not in C, the weight of those colorings is 0. And Korean's conjecture states that there is no graph satisfying GHZ state with more than 4 vertices and more than 3 colorings. Although GHZ state is quite famous, there are other quantum states that are also of interest. For example, the W state, where suppose we have n vertices, then C is defined to be all colorings with 1 red vertex and n-1 blue vertices. So here we show a graph that satisfies the W4 state. And we also have the DK state, which is a generalization of W state, where the colorings set C is defined to be all colorings with K red vertices and n-K blue vertices. And here is a graph that satisfies DK states too, because you can check all perfect matchings of this graph, and you will see that each perfect matching will give a vertex coloring with exactly 2 red vertices and 4 blue vertices. So the problem that we defined before involves the complex weight for edges, perfect matchings, and vertex colorings, which is quite challenging to solve. And in this study, we do research on a simplified setting of the problem defined before, and we consider the unweighted case. We still are given a set of vertex colorings C, and we want to ask if there is a graph which satisfies the following 2 conditions. First, for each coloring C in capital C, G has at least 1 perfect matching with that coloring C. And second, for each coloring C that is not in C, G has no perfect matching with that coloring. Note the difference between this unweighted version and the previous definition of the problem. The first condition can be viewed as a necessary condition of the weighted version, because in order to let C has a weight 1 in the weighted version, G must have at least 1 perfect matching with that coloring. But the second condition is a simplification, because in the unweighted version, we require G to have no perfect matching with the coloring C, while in the previous definition, G allows to have multiple perfect matchings, possibly with coloring C, but in the end, the weight of those perfect matchings should cancel out so that the coloring C has a weight 0. And the unweighted Korean conjecture over the GHZ state has been proven in 2017. And we have the observation that if a graph satisfies the unweighted version of the GHZ state, then there exists an edge weighting which makes the graph satisfies the GHZ state. And this observation is based on the fact that the perfect matchings which belong to different vertex colorings in GHZ states are disjoint. But this is not true for general quantum state. So whether the above observation is still hold is open for quantum states besides GHZ. So in this work, we propose some purely graph theoretic problem without considering the complex weight. And also we consider general quantum state not limited to GHZ. Since the original problem is graph construction problem or graph non-existence proving problem, which is quite challenging, we tackle first some decision problem as a first step towards the ultimate goal. So we define the problem PMVC, which stands for perfect matching under vertex coloring constraints. Given a graph G with bicolored edges and a set of vertex colorings capital C, we want to decide if the set of vertex colorings of G's perfect matching is exactly C. So this definition might read a little bit hard to digest. I will give an example, which is actually the GHZ state where C is defined by all monochromatic colorings in the case of 2 colors. Okay, suppose our graph has 6 vertices, and now I have 3 graphs here. We want to see which one satisfies the conditions of PMVC and which one doesn't. So the first one satisfies the condition because it has exactly 2 perfect matchings, where one of them gives the all red tolerance, and the second gives the all blue tolerance. And actually, this cycle shape with interchanging blue and red edges is a pattern that people can make GHZ graphs with arbitrarily even many vertices and two colors. And the second one doesn't satisfy the condition because it lacks a perfect matching with all blue colorings. The third one also doesn't satisfy because there's one more perfect matching with non-monochromatic vertex tolerance. So only the first graph provides a set of vertex tolerance of its perfect matchings that exactly matches the capital C. And here we also want to claim that if a graph with only real positive edge widths satisfies the quantum state, then it must satisfy the PMVC condition with respect to that quantum state. So it actually means PMVC is a necessary condition for the original weighted version of the problem if you restrict the weights to be real and positive. So in the rest of this presentation, I will be introducing our approach and attempts to tackle this decision problem. At the first glance, PMVC is one decision problem, but actually the two conditions make us decompose this problem into two separate decision ones. The first is called exist PMVC, and the second one is called for all PMVC. Exist PMVC wants to decide if a graph has a perfect matching with vertex tolerance C for each coloring that is not in capital C. And for all PMVC states that we want to verify G has at least one perfect matching with vertex tolerance C for each C that is in capital C. And it's not hard to see that the condition of PMVC is actually the intersection of for all PMVC, which means that for all tolerance that is in C, you must have at least one perfect matching in G. And also the negation of exists PMVC, which means for each tolerance C that is not in capital C, G must not have any perfect matchings. So if we can solve those two problems, decision problems separately, then we get an approach to tackle the original PMVC decision problem. And we attempt to tackle those two decision problems in two papers separately. We first studied the problem exists PMVC, and we found that it has a strong connection with a known graph theoretic problem called exact perfect matching. In exact perfect matching, or XPM, a graph is colored by blue and red edges. And here we do not consider bicolored edges. And we want to decide if G has a perfect matching with exactly K red vertices. Although perfect matching has been a well-known polynomial problem due to a Blossom algorithm, the complexity of XPM is open for more than 40 years. And it's one of the few problems that are very likely to be in polynomial time, but still not proven to be. And we found that exists PMVC, where C is represented by symmetric constraints, is polynomially equivalent with the exact perfect matching problem. And by symmetric constraints, we mean that whether a coloring is in capital C is totally defined by the number of different colors in that coloring. And C represented by symmetric constraints already cover a lot of interesting quantum state. For example, the states that we introduced before, GHZ state, W state, and the DK state, they all belong to the case that can be represented by symmetric constraints. Now that we have successfully connected exists PMVC with symmetric constraints with a known graph theoretic problem, XPM, can we just apply the algorithms for XPM to solve exists PMVC? It turns out that directly applying the XPM algorithms can yield insufficient algorithms for exists PMVC. So we designed more efficient algorithms specifically for exists PMVC with symmetric constraints on bicolored edges. We propose two lines of algorithms here. The first is based on symbolic matrix determinant, and the algorithm is randomized with complexity O n to the 2d plus 1, where d is the number of colors and n is the number of vertices. So this algorithm should be efficient on low number of colors. We also propose deterministic algorithms based on dynamic programming, which yields a complexity of n to the 2d times 2d plus 2 to the tree width plus 1. This algorithm should be efficient on graphs with low tree width. Overall, exists PMVC is relatively easier in the perspective of theory, as we connected it to XPM. And also we propose polynomial algorithms parameterized by the number of colors and the tree width. Those algorithms can still be slow. However, in practice, when the size of graph is large or the number of coloring is high or the tree width of the graph is high. So we aim to propose predictor algorithms based on Boolean logic and SAT solving. So what is SAT solving? SAT, or Boolean satisfiability problem, is one of the most well-known and earliest problem that was known to be NP hard. And in SAT, we have a bunch of Boolean variables that can only take value from 0 and 1. And we have a group of Boolean constraints, which can be represented by Boolean variables and Boolean connectives, including or, not, and XOR, and so on. And SAT solving is to find whether this group of constraints have a solution or prove the non-existence of such a solution. And the solution is a group of assignments to each variable such that all constraints are satisfied. So SAT solver either gives a solution or proves the unsatisfiability. And SAT solvers are usually considered as one of the most successful area in formal methods in the sense of engineering, because state-of-the-art SAT solvers currently are solving industrial instances with millions of variables, despite of the NP completeness of SAT solving. So let's see how we can solve exist PMVC with Boolean logic. And actually, the task is to encode exist PMVC into the format of SAT formula. And when it comes to perfect matching, the most natural way of encoding them is by exact one constraints. Exact one constraints works as follows. For each edge, we assign a Boolean variable to it. And for each vertex, we want to give an exact one constraint to all Boolean variables corresponding to the edges that are adjacent to that vertex. For example, for the vertex V, where E1, E2, and E3 are connected to it, we write this exact one E1, E2, and E3, which will enforce that among those three edges, exactly one edge will be chosen. And that corresponds to the fact that in a perfect matching, V will be covered exactly once. And if you list the exact one constraint for each vertex, and solve it, then you will have either a perfect matching or a proof of the non-existence of such a perfect matching. And we call the union of those constraints, exact one constraints, as ISPM. So solving exist PMVC with Boolean logic or SAT formula is quite straightforward. First, we assign a Boolean variable to each edge, and then we solve the following SAT formula by SAT solver. We just want to see that if there exists a perfect matching E and the coloring of E is not in C. So now let's turn to the second problem for all PMVC, which we found harder than exist PMVC. So in for all PMVC, we want to decide if G has at least one perfect matching with vertex coloring C for each coloring that is in capital C. This problem has no pure graph theoretic algorithm known. And physicists turn to enumerate all perfect matchings in a brute force way, which is not efficient because counting perfect matching is sharply complete. And a problem in sharply complete is considered strictly harder than NP complete. And also the number of perfect matchings in a graph can be exponential. And we try to solve this problem by Boolean logic. And the idea is that n Boolean variables can provide 2 to the n many Boolean assignments. So that provides us the power of absorbing exponentially many perfect matchings. We first studied the complexity of the problem, and we found that the complexity depends heavily on how you define the coloring set C. And we found that when C is of polynomial size, the problem is in P time, and the proof is quite straightforward because in that case, for each coloring C, you can check by polynomial perfect matching algorithms such as Blossom whether C has a perfect matching, and you can do that for all colorings in C. But the problem becomes significantly harder when C has exponential size. For example, for the decay state, which requires the number of red vertices to be k and the blue to be n minus k, can provide a coloring set with exponentially many colorings when k is unbounded. And the complexity in this case is still open. An open problem is to prove for all PMVC is W1 complete with respect to k on decay state. Despite of the mysterious complexity of for all PMVC in theory, we were able to tackle this problem in practice by SAT solving. So the problem is still how to encode for all PMVC in Boolean logic. Remember that we just introduced the exact one encoding of perfect matchings. But the problem is that the natural encoding with exact one constraints for perfect matching yields a long quantified Boolean formula, or QBF, which are quite hard to solve for the state-of-the-art solvers. The reason is that we need to write a formula in the form of for all colorings, and there exists a perfect matching. Or briefly, we can denote the formula above as for all coloring exists perfect matching. So it consists of two layers of quantifiers, first for all and second exists. So it's a quantified Boolean formula. One of the biggest contributions of our work is to eliminate the universal quantifier of the formula above and make the formula a purely existential one, which can be efficiently solved by stat solvers. And to achieve this, we first negate the formula above to get a formula in the form of exist coloring, not exist perfect matching. Non-existence symbol over perfect matching is a little bit uncommon in logic. It actually indicates that an encoding of the non-existence of perfect matching can give us a set encoding. However, it's not trivial to encode the non-existence of perfect matching in Boolean logic, although the existence of perfect matching is quite easy to encode. And that's where we need to use Tutt's theorem in graph theory to resolve the issue. Tutt's theorem is one of the most famous theoretical results in graph theory, which gives a necessary and sufficient condition of a graph having no perfect matching. So it says a graph has no perfect matching if and only if there exists a vertex set S such that G with S removed has more than the size of S many odd components. Here we still have an example. In this bipartite graph, which is unbalanced, there is clearly no perfect matching. But the two vertices on the top actually gives us a short proof of the graph having no perfect matching, because with those two vertices removed, G was left 4 odd components. And that's why vertex set S gives a short certificate of the non-existence of perfect matching, which we will exploit in our encoding. So in our set encoding, we search for a touch set under coloring constraints to reject the PMVC condition, as we just negated the formula. So our formula will look like exists colorings and exists a set of vertices such that the coloring is in capital C, as well as the vertices S is a touch set. And if the formula is satisfiable, then the graph violates the PMVC condition, as we find a coloring C such that the graph has no perfect matching with that coloring C. So looking back, we started from a quantified Boolean formula, or QBF, with both universal and the existential quantifier, which are quite hard to solve, to the negation form of that formula, which consists of this uncommon non-existence symbol. And finally, we remove this non-existence symbol to the existence of the touch set. And the set formula will search for it. It's time to show some experimental results. And we built some benchmarks for evaluation based on decay graphs. Remember that in decay graph, C is defined to be all colorings with K red vertices and N minus K blue vertices. And we can create graphs which satisfy decay state in this pattern. So we first generated some positive random samples that satisfy the decay state. And then we generated some non-decay graphs by removing edges from the decay graphs such that there will exist some colorings with K red vertices and N minus K blue vertices, but the graph has no perfect matching with that coloring. We first show some experimental results for verifying decay graphs for all PMVC condition. We implemented our approach based on touch encoding, and we also implemented some symmetry breaking constraints, and we name it as touch plus optimization. We also implemented the enumeration-based approach, and as well as the quantified Boolean formula-based approach. You can see that touch encoding with symmetry breaking constraints outperforms other methods with an exponential gap. Previous approaches can be quite slow when the number of vertices is over 25, while we significantly increased this limit to up to 40 vertices during the time limit of 1,000 seconds. So you may wonder whether 40 vertices is considered large enough. However, the application of those quantum graph problems are actually the preparation of resource state of measurement-based quantum computer, or MBQC, where people are still struggling with preparing quantum states with tens of nodes. So actually, 40 vertices is quite an improvement. We also want to emphasize that the optimization techniques over symmetric breaking constraints matters a lot. We also show some results regarding refuting non-DT graphs for all PMVC, where the stat solvers over the touch encoding should produce satisfiable by finding a touch set. And we generated non-DT graphs with 80 vertices. And we can see that touch encoding with symmetry breaking solves more instances than others during the same time limit. As expected, it shows the advantage of stat solvers in terms of searching. So in summary, we proposed and solved graph theoretic problems with quantum interest. We defined unweighted graph decision problems on arbitrary quantum states as a first step towards solving the weighted problems. And we studied the complexity of those problems and also proposed logic-based practical algorithms. And for future directions, first, in this work, we focused on solving decision problems. But in the future, we want to automatically construct graphs for arbitrary quantum state, either in the unweighted case or a weighted case. And second, we are also interested in solving other quantum circuit synthesis problems by logic-based approaches. With that, I conclude this talk, and you're welcome to read our papers, try our tools, and contact me if you have any questions. Thanks for listening. Here is the reference of this presentation.